Hi, today we will talk about the multiply excited electromechanical energy devices and also how to couple them with some mechanical systems. So let's again start with the review from last week. So what we have seen so far is if you have this has to be like a linear system here. In linear system we need to take the derivative of the inductance or reluctance, so all those devices moves in the direction of to the minimum reluctance position or similarly maximum inductance position. Okay, so if there's a change of inductance with respect to displacement, there will be some force. If the inductance is constant, if it's not changing with position, then there will not be any force. And this was for linear systems. And for rotational systems, the only difference is like we were taking the derivative with respect to rotation, not displacement. So d theta is the displacement of that angle. So similarly, nothing changes. Instead of taking the derivatives with respect to x, we are taking with respect to angle, and instead of force, instead of newtons, we have torque, Newton meters. Okay, so all other characteristics are same. So the things rotate in the direction to the minimum reluctance. Okay, so I will show you a couple of examples, and I want you to guess which direction is it rotating, or if it is rotating at all. And then, like the difference to the previous week, now we have two coils, so that is the definition of multiply excited system. You will have more than one current or voltage source, more than one electrical port. And let's see. So here, let's say we have the first coil on that side, and that is, let's say we have an iron core, and here again that one is iron, and in that one we have the second coil, instead of the iron core. We will talk about that later. So what happens if we excite only the first coil, right? If we excite just the first coil, the rotor is perfectly cylindrical, okay, and the air gap is not changing. So if you define the reluctance with respect to angle, it will be constant, and also the inductance with respect to that angle will be constant. And as it is constant, the derivative of the reluctance is 0, and the derivative of inductance with respect to position is 0. Therefore, you will not get any torque from this system. Okay, even if you just excite coil 1 just itself, or just coil 2, there will be no force, no torque. Okay, we will talk about what happens if we excite both of those systems later on the slides, but now we are just looking at if it is a singly excited system. Okay, so here, like we have a similar system, but now we have not a perfect circular air gap, so it has like a short air gap here, but it has like air here. So that part is again iron, so that part is iron. So here it is like small air gap, but on that side there's a larger air gap. So again, what happens if I just excite coil number 1? If I just excite coil number 1, okay, from the point of coil number 1, or let me write it like L11, okay, if you think L11 or the reluctance of the first coil, so even if you rotate that system, it is again cylindrical, and even if you rotate it, the air gap or the reluctance, therefore the inductance, is not going to change. So I can say that one is constant. So no torque, let me write here, no torque if only coil number 1 is excited. Okay, so this is from the perspective of coil number 1. So what happens if we just excite? So let me write it, coil number 1. Okay, so for coil number 2, so there's a different story here, because if it is in that direction, okay, if it is in that direction, again it's not shown in the graph, but you can think all that thing is combined with an iron core. Okay, so the flux, let me use the orange, so here it will try to go back through here, but somehow if it aligns itself vertically, so suddenly it has a shorter path of air, and we assume in this one iron is like infinitely permeable. Even it is not infinitely permeable, it is like much more permeable than air, so it will be less reluctance. It is much easier, okay, it is less easier for flux to travel when the coil 2 is aligned vertically. Okay, so L11 or L11 is not constant, okay, and sorry, not 11, it is L22. I will say why it is, let me say 22 but not 2. Anyway, R2, okay, theta is minimum when rotor is vertical, or in other words, theta is equal 0. Okay, so it will create, okay, when you excite the second coil, just the second coil, it will try to align itself vertically with the magnetic core, and here coil 2 is excited but coil 1 is off. Okay, so it will rotate counterclockwise. Okay, cool. So let's move forward. So what about in this case? So here, and we have the iron, and now it is not a cylindrical rotor as in the previous case, but this is the rotor, this is the iron bit. Okay, so the rest is here, that part is air. Okay, and we have coil number 1 and coil number 2. So now if coil number 1, okay, is excited, then what will happen? Actually, again, it will try to align itself to the minimum reluctance position at the flux. Okay, so here maybe the flux would like to travel like that from coil number 1, and it is, I don't know, coming like that way and then coming back. Okay, maybe like that. Okay, so it tries to actually minimize the path that is going through air, because it is like a longer resistance or higher reluctance position. So it will try to align itself again to the minimum reluctance position. Okay, so let me write it here. So R1 theta is minimum again when the rotor is vertically aligned. So in other words, theta is 0. So again, it will rotate in the counterclockwise direction, and if you just keep giving a DC current, so it will, if there is no friction, it will rotate, come back, rotate, and it will do that kind of oscillation. If there is some friction, then the oscillation will be damped and it will align vertically. And again, the direction of rotation doesn't change even if you apply a negative current, because the torque, remember, the torque equation is proportional with the square of the current. So the direction of the current has no effect directly on the direction of the torque. So what happens if coil number 2 is excited only? So again, from that perspective, I mean, the other areas are air. So yes, there is some iron. So you have some coil, let's say around this pencil, and everything around it's air. Yes, the flux will concentrate on the iron itself, but even if you rotate, the coil number 2 is rotating with the plunger, with the pen here. So the flux direction, the all flux is rotating, but the total reluctance or total inductance is not changing. So R2 theta is constant, right? So, and it's constant, then there will be no torque for this case, right? So then, I mean, that is the topic of today's lecture. So what happens if both of these coils are excited? Okay, so now in the previous week, what we have seen is, yes, you have a coil number 1. So there's like the similar case of that one. Okay, so you have the coil number 1, and there's some rotor or plunger that can rotate around its axis. So it can rotate like that. And again, if you just ignore coil number 2, and if you excite coil number 1, so it will try to move to the minimum reluctance position. It will try to align itself. But now, like, we have 2 coils. So what happens if those coils, torque directions are opposing each other, or how we can define the total overall cost? Can we just calculate it from the torque generated from that one and from that one? Actually, in order to do that, let's go back to our definition. So again, the relation between the electromechanical and the mechanical systems are through the magnetic storage, right? So first you need to convert the electrical energy to magnetic energy by storing it, or in other words, increasing the flux density. So in order to have some mechanical force, so you need to have some kind of inductance, which always there is some inductance, even if it is a straight line. Anyway, then the magnetic energy is converted to the mechanical energy, because again the system tries to minimize its overall energy. So remember what is happening. So what you have is, in a singly excited system, it can be like BH or whatever flux and MMF, whatever you call it. So you can have that kind of operating system. So that area was the stored energy or stored energy density, and the system would like to move in that direction. So in that way you can minimize its energy, and the area, let me use another color, so the area between, okay, if it is moved in that direction and if B is constant, so this is converted right here, converted to mechanical energy. Okay, let me, I think it was out of the, this is the MMF. Okay, so here we have the same thing, but instead of, like, if you think it's like a swimming pool, instead of having a single pipe, water pipe feeding the swimming pool, we have 2 of those things. So 2 of those are filling the swimming pool, and I have a single outlet which is still the mechanical energy. So the question should be, how can I calculate the magnetic energy in that system, right? So let's go back to the definition of the mutual inductance. So again, in order to write, normally if it is just a single coil, okay, what you can write is VL is equal L times di over dt, right? So the inductance, or again inductance, is the flux linkage created per current, and the voltage here is like the derivative of the current from one coil, and you multiply it by the inductance. So what happens if you have like 2 coils like that, and I would like to write the voltage of that equation? So in other words, if let's say IL2 is equal to 0, should I get a voltage? I mean, depending on that equation, no. But of course, what we know is if you have another coil and if it is creating some magnetic flux, and if some part of that magnetic flux is linking to the other coil, so in this case it is the green arrow, so the flux created by the first coil actually links the second coil, so therefore you can get some voltage on the second coil. And actually that was the whole idea about the transformers, right? So you have two coils, they are connected by a magnetic core, so you excite the first coil, but you can have some voltage in the second coil. So that is all about it. So what is the second coil's voltage? So it is not only like L times di2, L2 di2 over dt, okay, VL2. It is plus the amount of flux linking the coil, so it is either L1, 2, from 1 to 2, or that one is called the mutual inductance. We can use the letter M, and times di1 over dt, right? So you can still generate some voltage from the second coil if the current in the first coil is a time varying signal. If this is constant DC, yes, there will be some flux linking to the second coil, but in order to generate some voltage, it has to be changing with time. Okay, so what is the stored energy in those coils? Okay, so again, if it were just normal a single coil, what you can write is 1 over 2 I square L, and that was correct for single coil. If you have like more than one coil, that definition is not correct. So let's write the total energy, change of energy. Change of energy in this case is I1 d lambda 1, but the flux, okay, the flux passing through that coil, or that coil, it doesn't really matter, is not equal to just the flux created by the coil itself. There is also some coupling between these two coils. So how can I write that flux linkage is L11 self-inductance times di1 plus, this is the inductance between the first coil and the second coil, or that one is called the mutual inductance. Okay, so and multiplied by di2, because again the amount of, if there is no current in the second coil, in one of those coils, so the system behaves like a singly excited system, and in that one that cancels it as well. Okay, let me up. So let's write those things. So if this is the flux in the first coil, or if this is the energy stored in the first coil, okay, I can write the same for the second coil, because in order to find the total energy in the system, I would like to calculate all those B distributions, or all those flux created by both of the coils. Okay, so anyway, if you write that thing explicitly, let me write it here more explicitly. I mean, yes, that is, you know, the derivative or the change, you can think is like delta, and if you just integrate it from where to where, 0 to I1 or 0 to I2. So you start from zero current, okay, so you start from zero current, at the end of the day you have both of the coils excited. So if you integrate all those parts, you can get the total energy, right? So again, you know, what you can write here, I mean, or if that one is like confusing for you, what you can think, if it is a electrical system and if there is no electrical loss, what you can think is the amount of electrical energy I have given to the system is converted to the mechanical energy. So maybe you can feel more comfortable with that definition. You can write Vi over dt, whatever, from 0 to T, so that is the power that you are supplying to the system, so you can integrate it over some time. Okay, so what you can write for the first coil, like V1 E1, you can write for the first coil is L11 times di1 over dt. Okay, this is the voltage plus, and this is not the voltage of the first coil, there's also the mutual inductance, so you can write this L12 times di2 over dt. So this is the voltage part times I1 times, I think that was out of the dt, right? So if you integrate it, what you are going to find, I mean, just for this part, this is coil number 1, okay, so it is 1 over 2 L11 I1 square as we know it, plus 1 over 2, okay, L22 I2 square, sorry, it's not that one, L12 times I1 times I2. Okay, so that will be the effect of the mutual, and you can write the same thing for the second coil. Let me write it here for the second coil. Okay, and it will be 1 over 2 L22 I2 square plus 1 over 2 L12 or L21, but they are equal, it's a symmetrical system, I1 times I2. And if you add these two, okay, what you are going to obtain is that equation, right? So that is the total stored energy if you have more than one coil. So again, it is kind of straightforward. The first one is normal self-inductance, stored energy in the self-inductance. L11 shows the self-inductance, and the second one is the energy stored in the self-inductance of coil number 2, so it is proportional with the square of the I2. And there is 1 over L12 I1 times I1, that term. And there's another term, 1 over 2 L21 I1 I2. Okay, and again, since it is symmetrical system, L12 and L21 are equal to each other because the geometry is same. And you can write these two are added up, it becomes L12, or let me write here, L12 is equal to L21, that one is equal to mutual inductance, and you get rid of the 1 over 2 term, and that is the equation that you have. That is the total stored energy in a multiply excited system. I mean, once you are comfortable with that, the rest is easy. But first, let me put that one into a matrix form. Okay, so I mean, all the equation that I have written here can be written like in the matrix form. So total stored energy, you can, it is the transpose of the current matrix and current matrix, and this is called the inductance matrix. I mean, probably you will not need that one if you have just 2 coils, but let's say I will show you an example. Let's say you have 6-8 coils. Okay, all of them are linking to each other. Then instead of dealing with all those equations separately, it is easier to put them all in an matrix form. Anyway, so you can actually combine that one, so it becomes 1 over transpose of current inductance matrix times I. So it just gives you that equation. Okay, don't worry about it. But I will show you a case, but first let's have a look at how that can be implemented. Okay, so I will show you a video of a contactless surgery using that kind of coils and electromechanical energy converter. Okay, so this is called Octo-Mech. Okay, Octo is for 8, and it is a 5 degree of freedom wireless manipulation for some surgeries inside your eye. Okay, so what they are doing here is they are injecting a really small device like that. So it is, you know, it's the iron piece you can think of. So it has some permeability. Okay. So it can be moved inside your eyes, make the surgery, you know, cut those things. And how it is done? It is done by, you know, those 1, 2, 3, 4, 5, 6, 7, I think another one here, 8 coils here. So they are, you know, giving some specific currents to those coils, and your head is placed just inside here in the center, and by just, you know, exciting all those things differently, then you will be able to calculate force. Okay, so in other words, they have by 8 by 8 matrix, which, you know, all those inductances can be measured, and the problem becomes like, in order to move my needle or my small cutter from one position to another, how much current should I give? So it just becomes a matrix solution, my matrix equation. So if you can solve it for specific currents, you can calculate those things. Okay, so let's go back to video. So here, I don't know, so it is just like moving. So I don't know if it is clear from here. What you can see here, okay, what you can see here is the direction of the 8 coils currents. Okay, so the software is calculating, and this is like moving inside that one. So here again, this is the real case. Okay, let me it's the real case, and here it is the magnetic field direction, so B field direction, and this is the again the currents of individual coils. Okay, see how it moves in the simulation in reality, and please have a look at the coils current directions. Okay. So again, I think they are putting, just to increase the, you know, force generated in that one, they are thinking of adding a permanent magnet or using different materials, and they are talking about those things. A magnet. So here again, they can rotate it. I mean, just keeping the tip of that thing constant in space, and they can move it in all directions. Anyway, so you can have a look at yourselves later on. The link is on the presentation file. Okay, so then the question is, okay, yes, we have the energy, but how we can generate the force? So again, the same equation is still valid. So the system again tries to minimize the stored energy. It likes to move in the direction that minimizes the stored magnetic energy. So in order to calculate the torque, or in order to calculate the force, I need to take the derivative of that equation, or I need to take the derivative of that equation. So suddenly it becomes, you need to take derivative of the inductance, second inductance, and the mutual inductance. Okay, so that is the important equation. So that is I1 square, I2 square, I1, and multiplied by I2. So there's, you know, this equation is just the derivative of the magnetic energy. But there's one interesting part. As we have seen, like in the previous week and on the first equations, so the torque is proportional with the square of the current. So even if you are giving 5 amps or minus 5 amps, it doesn't make a difference, because you are taking the square of that thing. So the direction of that component is only controlled or only determined by the derivative of the inductance. So the current direction has no effect on the torque direction. The same is true for that one. But they are quite interesting in the mutual inductance term. Yes, the force direction is still dependent on the derivative of the mutual inductance. But if you give like 5 amps to the first coil and like minus 5 amps to the second coil, that multiplication, okay, can be positive or negative. So by controlling the current directions, actually it will be, possible to rotate the rotor or create a torque in the opposite direction. So that is, really useful in, electric motors. You don't want to just go in one direction, but sometimes you want to rotate the motor in the other direction, or there can be some linear systems as well. So by using mutual systems, it gives us more control. But that doesn't mean sometimes like self-inductance would like to rotate our system in clockwise direction, and maybe mutual inductance will try to rotate it in the opposite direction. Okay, so let's go back and like have a look at our examples. And again, this is the generalized term. Again, nothing has changed, and you have the current. Again, it just gives you that equation, and you have to take the derivative of the matrix, and actually that is the old equation behind that octomech, that eye surgery thing, where you have the coils. So you have in one position and you want to go to the second position, so you can calculate how much torque should I generate, and in order to calculate how much torque that you should generate, once you know those things, from the system geometry, you can calculate what should be each coil's currents. Okay, so let's go back to the same examples, and let's write it like more systematically, and let's see what happens if we excite both of those coils. If the coil 1 and coil 2 are excited at the same time, what is the resultant torque? Again, let's have a look at that system. So in the first case, remember, this was perfectly cylindrical, and there were no, the change of L11 with respect to angle, it was constant. Okay, and again L22 with respect to angle, it was also constant. Okay, well, what about the mutual flux? Again, if I have like 2 coils like that close to each other, they will have the maximum mutual inductance. And if I put them like at 90 degrees like that, the coils are in that direction, yes, probably will have like minimum mutual inductance magnitude. But if I put them like that, that is another important thing. Inductance, normal self-inductance cannot be negative, right? So there is always some positive inductance. But for mutual inductance, depending on the orientation of the coil, the mutual inductance can be negative as well. So, again, in this case, the system will try to move to the direction to maximize the self-inductance of the coil number 1, coil number 2, or maximize the mutual inductance. And the rotation doesn't change the self-inductance of coil number 1, or doesn't change the self-inductance of coil number 2. But if I rotate in that direction, then the coils will be aligned. So that way, all the flux I generated from coil number 2 will link the coil number 1, not all, but let's say maximum value. And similarly, most of the flux generated in the coil number 1 will link the second coil. So again, if I just write that one, then that term will be 0 because it is not changing with position. That term will be 0, and I will end up just with the third term. Okay, the torque it is generated is I1 I2 times the derivative of the mutual inductance. Okay, and again, if let's say the direction of the coil number 1 current and coil number 2 current are same, so it will then try to align itself in that direction. But somehow if I apply a negative current either to the coil number 1 or coil number 2, as you can see from the equation, if I reverse that one, okay, and then the torque will be reversed. Okay. Okay, so let's move to our next example. So here, remember again, compared to like L11, it was constant, and L12 theta was not constant. So therefore, some L12 generates torque, right? But so we have still the first component, okay, the self-inductance of coil number 2. Sorry, I have written it like wrong. It should be L22. L22 self-inductance of coil number 2 generates a torque, and its direction is not depending on the direction of the current. Okay. On top of that, then I will have the mutual inductance term, I1 times I2 with respect to delta M delta T. Okay, again, those two components can work together or can oppose each other. Okay. Okay, so let's move to the next one. So here, I mean, it is the vice versa. So here, L22 was constant. Okay, so the derivative of that one with respect to angle is 0. So there will be no torque depending on the L22. But in this case, now the first coil will try to align itself with that salient pole rotor, right? And on top of that, then we will have the mutual inductance as well. Again, you know, that one is always moving in the direction to maximize inductance, but that one, you know, can its own direction from the mutual inductance term, but depending on the polarities of I1 and I2, you can generate some torques in the both directions. Actually, your first homework will be based on that topic, so you will see some other examples. Okay, so this was the part with the magnetic system, but at the end of the day, all of those things are coupled to the mechanical systems. Okay, and I mean, before moving on forward, I would like to do a short review. Again, displacement, where you have like that one, this is displacement, so it is how much you move. It's in meters, and in rotational systems it is in radians. Okay, or you can have like speed or velocity. You can have linear velocity, meter per second, or you can have angular velocity shown by omega, radian per seconds, or that can be in practical applications. There will be some different units like RPMs, rotations per minutes, that kind of things. But in normal mechanical system, or the SI unit for equations is the radian per second, so don't get confused. Okay, so again we have the force is like newtons, and the equivalent of that in rotational systems is torque. And you can have mass. Okay, so remember, like in kinetic system, in a linear system is 1/2 mv square. Okay, kinetic energy, and in rotational systems it is 1/2 j omega square. So it is, or you can write power is equal to force times velocity. Okay, and torque is equal to power is equal to torque times omega. Or, you know, similarly, what you can write is F is equal ma, okay, and torque is equal J times d omega over dt. Okay, these are all equivalent relations between these two. So here I have F is equal to ma, or derivative of the velocity, and for the rotational system I have torque is equal to J times d omega over dt. So if you have a large inertia system, for the same torque it will take longer to increase its speed. Okay, so probably you already know those things. And similar to what we have like dynamic equations or second order equations in electrical system, there's similar equivalents in the mechanical systems. And the first one is like you can have some force in the HTML version. You can have the animated versions of these figures. So by increasing by applying some force, there will be some displacement in the spring. Okay, so it is spring constant, so it is K times delta X. Similarly, in a linear system, you can have some spring systems in the linear system. So depending on how much torque you are applying, there can be some displacement. And there's maybe less familiar with you is the damping. Okay, so damping is a term. So it is like friction, but it's not like static friction. So it's called the damping. So damping is proportional. It's usually shown by B. So it is completely similar to, again, please have a look at the animated version of that one, and also click on the videos of those links. So if the system is like that one, overdamped, so it starts moving back and forth, there's some spring. And if there's no damping and if there's no friction, if you just excite a spring system, it will just go up and down or sideways and infinitely, right? But once you have damping, so this is the damping's schematic, so it is usually shown like a piston inside a cylinder. So once you have damping and force is proportional to the speed, linear speed, or the rate of change of that one, so actually it dissipates some energy and it will damp the system. So in our system it's like resistive components. Okay, so again in the dynamic equations what we have is like F is equal to ma, like dv by dt, or the second derivative of the displacement. And suddenly if you just put everything here, it is no different than writing an RLC circuit. So mechanical force is equal to m times a, so this is acceleration, okay, acceleration, and b times this is velocity, and k times, so this is displacement, plus some constant speed. So it is actually really similar to a second order differential equation, right? So the interesting things, why it is important for us is at the end of the day, yes, we are generating some electromagnetic force or torque, we are running our motor, we are rotating our satellites, whatever you do, but that force is going to couple or have some interface with a mechanical system, right? So they will actually, there's some force with respect to your current, displacement, maybe your magnetic systems, the materials are not linear, and on top of that you will have a maybe non-linear system in the mechanical side as well. So you need to solve all that equations as a system, and it is really important from the engineering point of view. You have to consider, you cannot say I'm not a mechanical engineer, it is not my job. Yes, maybe mechanical engineers will have more detailed analysis on that part, but at the end of the day, as an electrical engineer, you need to understand the mechanical system so you can control your electrical system properly. Okay, so I would like to show you a nice example for that one. This is from, again, Bose. This is the same Bose, remember from the last week, the headphones company. Actually, Amar Bose thought, I'm making speakers, so it is a linear actuator. Why can't I make a actuator for electric cars, so active suspension system. So the idea is, instead of just, because in a normal car you have springs or hydraulic dampers, they are also called dampers, so you have no active control. So what he proposed is to use a linear electromagnetic motor, or a system that generates electromagnetic force, and it is connected to the wheel. So let me show you what happens with that system. Okay, so we have that system. So one of the cars has the electromagnetic suspension and the other one is just normal. Again, the links are in the presentation file. So let me go with that one. So they are going some humps, speed bumps. Okay, so it's doing a simple test. And this is the original suspension, you know, designed by Bose in 70s or 80s.
Same model, same everything, except completely modified suspension system.
It's doing brake, and that one is more dramatic, I think. So it is like as if it is like floating through the speed bump, right? So it seems like it's not touching the bumps at all. So I think there are more dramatic photos. You see? Let me go back. Again, it will be like really useful. Let me show the previous one. It will be really useful for meteorite. Oops. So again, that one is quite nice. So it is coming. First they are, you know, reducing the height of the suspension, then they suddenly release because they have some active control, right? So they actually make it jump through.
You know, it's funny, right after we did it the very first time I
Okay, so again, you can have a look at in the links. But unfortunately, again, you know, having a nice technical systems doesn't always come with the economic success. I think due to increased cost or maybe increased control problems, I think that wasn't produced at that time. But I know there are some brands that are using now active suspension system, maybe using hydraulics and linear systems as well. But then Bose, I think they came up with a better idea. They came up with why I am moving all the car up and down instead of just like moving the driver's seat. So especially for, I think, truck drivers, please have a look at, you know, those links. Okay, so they have the same active suspension in the chair, like the driver seat. So when you are going over a bump, you are just moving up and down, so like you are as if you are not moving at all. So please have a look at those links as well. So I mean, to summarize, like multiply excited system, they are still behaving the same way. They are still tries to minimize the total stored magnetic energy, or they would like to minimize the reluctance and maximize the inductance. The only difference is now it is not the sum of two inductance energies. There is also some mutual coupling between, and that mutual coupling effect, you know, can generate torque even if there is no torque generated by the, you know, self inductances of the coils. The mutual inductance can generate some torque, and on top of that, because that term is related not with the square, like as if the self inductance is I1 square or the second coil is I2 square, the mutual inductance term is proportional with I1 times I2, and if you control the direction of those currents, it is possible to generate torque in both directions, which is useful with AC machines, as we will see in the following weeks. Okay, so that's all for this week. Thank you.